Hello, my name is Geuel Simiyu. I am a senior biology major and chemistry minor, and in the last year I completed an honors thesis titled The Characterization of Lipid Nanodisks Encased by Zwitter Ionic Styrene Malic Amide Copolymers, or ZSMA, under the instruction of Dr. Hanjin Liang and Elizabeth Kamilar. So the point of the research that I will be talking about today is to make improvements to the technologies that will help us to better understand membrane proteins. As you may know, membrane proteins are the gatekeepers of a cell, meaning they dictate what comes in and out of the cell. So they have also been linked to diseases such as cystic fibrosis, cerebral palsy, and neurodegenerative diseases like Alzheimer's and dementia. So they must be very important for us to understand, and what makes them difficult to study is their amphipathic nature, which means they have both water-loving and water-hating sections. And we must, in order to isolate them, we must find a medium that can support both of these polar opposite sections. And the best way to do this is to use membrane mimetic systems. The mimetic system we'll be talking about today is the nanodisk. So a nanodisk basically is a phospholipid bilayer, much like the one seen in actual cell membranes, that is stabilized by something. It could be a protein. In this case, this is stabilized by a membrane scaffold protein, or it could be a polymer. In this case, it's stabilized by the SMA polymer, which we'll be talking about shortly. As you can imagine, the membrane protein can be embedded in these tiny patches and isolated from anything else that can cause interference during measurements or anything. So we can observe the function of the protein, the structure of the protein, and essentially increase our understanding of the protein of interest. So we will be focusing on polymer stabilized nanodisks. So the polymer stabilized nanodisks were first created using the styrene malic acid copolymers. However, after their creation, it was found that they don't work well in low pH environments as well as in high salt concentrations. So our lab developed a new family of polymers, which was an improvement to the SMA polymer, in order to attempt to solve these issues that were seen in the SMA polymer. In order to do this, we created nanodisks using both of these polymers. So the one that we'll be specifically looking at is the Zwitter Ionic Styrene Malic Amide lipid particles. It's another way of saying nanodisks created using ZSMA. And in order to test how these two membrane proteins can isolate different proteins, we use the halarhodopsin HR protein, which is a 7-transmembrane receptor protein, and an MSBA protein, which is a 12-transmembrane helix homodimer, which is larger than the HR protein. We also used different polymers. We used the SMA, which was our control, and the different classes of ZSMA. So what we found was that it was shown that 2-to-1 ZSMA was the most efficient at solubilization, and the 2-to-1 ratio essentially just refers to the ratio between styrene and maleic amide within the actual polymer. We also found that ZSMA showed improved solubilization capability compared to SMA and MZSMA in the following criteria. So in low pH environments and high salt concentrations. And if you can remember back, this is essentially what the goal of creating this ZSMA polymer was. So it was very successful in that front. And we also found that ZSMA showed improved solubilization capability of crude membranes compared to SMA and MZSMA. So crude membrane is referring to a native membrane. So it's not an artificially created one, it's one that occurs in nature. That is it. I do want to acknowledge a few people who helped during this process. I want to say thank you to my thesis director, Dr. Hanjin Liang, my second reader, Elizabeth Camilar, and my thesis instructors, Dr. Caswell and Dr. Hodes, and the Texas Tech Honors College and the Texas Tech University as a whole. Thank you.